Hey Google, change the light color to soft white. Got about a minute. Oh, no. All right, greetings, scholars. Let me give myself some power. Yeah, so last week I just was not able to join due to technical difficulties out of my control. It was completely out of my control. So I guess the system was down or whatever for me personally. I don't know if it was like that for everybody, but for me, I just couldn't get in. I couldn't even send a message or anything. So I was like, oh, well. So we quote unquote lost a day, which was last Wednesday. So last week we were supposed to do 3-3 and 3-4. So there's a couple of things with that. So the way I have the schedule kind of designed, we kind of have like a few extra days, especially during exam week. We kind of have like a couple of flex days. So what I decided to do is, even though I do expect you to still use my recordings, right? I shouldn't have to say that because again, I couldn't get a message. I was trying to get a message to you all, couldn't even do that. But as a default, if for whatever reason, if we don't meet, even if we do meet, I still expect you to use my recordings and honor the schedule that's as outlined in Pearson. So that being said, I think that 3-3 and 3-4 would do right now. So there's a minimal late penalty, and plus those recordings, like I say this like every meeting, use my recordings. Like I keep saying, use them because those have the full details. It pretty much says the same things that I would say live. It's just like being in class. You write down your questions, anything that's not clear, and you reach out to me. I do have an office cell phone, so you can always call me. That works. That's something separate, so that works. So today I'll do a courtesy lecture where we'll do a makeup because again, 3-3 and 3-4 is already in the recordings. So those have been there since the beginning. You don't have to wait on me on this content. I just do these live sessions kind of like as a courtesy. But all the stuff I'm saying live is already in those recordings. So normally, let me see. Last week on Wednesday, we would have done 3-3 and 3-4. So we would have done 3-5 today and 3-6 on Wednesday. So what I probably do is do 3-3 and 3-4 today, just as a makeup lecture, and then it's going to be an accelerated 3-5 and 3-6. Usually 3-5 is one lecture all by itself, and 3-6 is one lecture all by itself. But I'm just going to kind of go through them a little bit quickly on Wednesday. And again, anything that I skip when we're together, again, I can't stress it enough. You have to use my recordings to stay on task. That's the whole point, because being remote, it does have technical difficulties. Oftentimes things that are out of our control, and I acknowledge that for you all as well. I stopped trying to sift through, like, okay, this person being genuine or not. So I kind of designed it where there is a fail-safe automatically built in when we have technical difficulties, right? So if I'm having trouble, if you're having trouble or whatever, right? So at a baseline, the main thing that I need from you all, especially when we're live, just get your attendance at a minimum. Just be sure to get your attendance. So obviously last Wednesday, I wasn't there, so you don't have to worry about last Wednesday. And keep in mind that attendance when we do these live sessions, it is recorded automatically, right? So all I do, I just log in, it records it, and then when class is over, I just go through the list. And pretty much if you were here, I've been giving people credit. I haven't been stressing too much about when people show up, but if I notice that people are showing up late, then I'll start to stress it a little bit more. But for generally speaking, as long as you're here, I've been giving you credit. And the other thing is, you got to be sure. You got to be sure that your Zoom username is your Morehouse student name, because when I go to record attendance, if it says Zoom user, I don't know who that is. Right. So you don't really want to be in that boat. The simple thing is just make sure it says your name, show up, and you can zen out. Just listen. Try to pick up on concepts as best you can. Ask questions if needed. And then just do your best to try to get the assignment submitted promptly. And again, with all of our assignments, I think we have unlimited attempts. The system is set to take your highest score, and there's a minimal late penalty. It's only like 5% to 10%. So what that means is, even if you submit something at the very end of the semester super late, you can still earn up to either 95% or 90%, at least 90% on most assignments. This is an A-. So again, if you want to like get above 90 or 95, then you submit things on time. If you can take the hit and you want to, give yourself a little bit of a cushion, then, you're adults. I'll let you work it as you see fit. Again, if you have questions, feel free to either type it in the chat or in the Q&A. We'll be sure to get them addressed, or feel free to unmute yourself and we can talk about it. And so the goal for today, we're going to spend time to go through sections 3.3 and 3.4. And then on Wednesday, we'll do our best to go through 3.5 and 3.6, and that'll get us back on track. Let me see. So an hour, 15 minutes. So we got about an hour. Let's just do 30. Okay. Hey, Google, set an alarm for 6:40 p.m.
All right. Your alarm's set for 6:40 p.m.
So at least I know that's approximately the halfway mark, and we can kind of go from there. Okay. So hopefully you guys are, hanging in there. All right. And again, the way I kind of designed everything in Pearson, there's an automatic extension and there's a minimal late penalty and unlimited attempts. So, but that little combo should be enough. Even if we have any kind of hiccups, you can still kind of work it. I've honestly had students, which I don't recommend, but I've definitely had students that procrastinate until like the last couple of weeks of school, and then they submit everything. And I was like, okay, well, then it's kind of like, obviously I'm not going to dock them. I acknowledge that the system that's built into the system, but I try to discourage students from doing that, just because if something goes wrong, and because, if something goes wrong, then you're screwed. As we get closer to like the finals, Pearson's server tends to slow down because, students worldwide are all logging in approximately at the same time. And then it causes their servers to be overrun. It just becomes more unreliable the closer we get to final. So the recommendation is you want to try to finish this stuff as soon as possible. Honestly, you can go ahead and finish all the homework for the semester right now and just be waiting on the exams. I think we got exam 2 and the final. All right, so that's all that we're going to have left. Okay, so I think that's it for our morning announcements. Again, if you have questions, feel free to either unmute yourself to get my attention or type in the Q&A or the chat, and we'll make sure to get your concerns addressed. Another thing about attendance real quick, don't stress too much about the attendance. Do the best you can. When I say don't stress, like, it doesn't affect your grade. It only kind of affects you if you accumulate like about 4 or more unexcused absences. Once you start hitting like 4 or 5 unexcused absences, then that's when it kind of you can be dropped from the course. You may or may not be able to get back in. You may or may not be able to get you probably won't be able to get a refund. Morehouse is infamous for not giving refunds and stuff like that. But so it's not going to affect your grade directly. It's really just a log. It's just something. Sometimes administrators come snooping. They're like, "Hey, when was the last time you saw so and so?" So now I just go to my records. And I'm like, "This is the last time that I had him on file, right? When I had him showing up or so on, right?" So it doesn't affect your grade directly. It only becomes an issue when you accumulate like 4 or more unexcused absences. Okay. So all right. So let's continue. So let's kind of recap some of the concepts and that we've been discussing. So obviously, so far for the entire semester, everything has been centered around the derivatives, right? I think we say this like literally every class. The derivative is the slope of a tangent line at a point, essentially, right? For our discussion. So derivative just gives you the slope of a tangent line, right? We introduced derivative with the limit as h tends to 0 of the difference quotient definition. Then we explore some more sophisticated techniques with the differentiation techniques. So like the product rule, quotient rule, chain rule, power rule, uh, extended chain rule or whatever. So that long technique that we have for finding the derivative, we could look at it and just write the answer, right? So we explore a lot of techniques like that. Last time, so we started to dive deeper into higher order derivatives and what they mean as far as functions and graphs, right? So I want to say that with the first derivative, remember the derivative is a slope of a tangent line at a point, right? If that slope is positive, then which means the first derivative is positive, that means the original function is increasing over that open interval, right? So we had the first derivative test, we had the second derivative test. The first derivative test, again, tells us whether the original function is increasing, whether it's decreasing, or whether it's like a relative max or a relative min, right? So the relative max or the relative min those are our critical values. Those are gonna occur when the first derivative is either 0 or undefined, and then you have, the sign change of the first derivative on either side of the critical value, right? So we had this whole process that we did for the first derivative test. The second derivative test was a similar process. So once you get, it's kind of like a twofer. Once you get one, you get 2 for 1 or whatever. But what the second derivative tells us is concavity, right? If the second derivative is positive, that means what? The original function is concave up, which means that it's like a cup that's opening up, like you can pour water into the cup because it's opening upward. So a positive second derivative means the original function is concave up, right? A negative second derivative means the original function is concave down. It's like your cup is upside down and you dumped out the water, right? And so then the critical point or the critical value for the second derivative, that's going to identify our point of inflection, right? Point of inflection is where the original graph goes from concave up to concave down or vice versa, right? And so those, again, just like the first derivative test, the critical value for the second derivative test is going to occur when the second derivative is either 0 or undefined. And then you got to, either test the sign of the second derivative on either side. There was also an extended test for the second derivative to identify our relative max and min. If we only had one critical value on some open interval and the second derivative of that critical value was like, that was either positive or negative, that would tell us whether that critical value was either a max or a min, right? So that's a decent summary of where we left off before we missed last Wednesday. Hopefully you were able to process all that. I know I was talking a little bit fast, but something should have got through. It's okay if all of it doesn't go through. Just something. Try to maximize, whatever you can. Okay. So that brings us to where we are today. We're going to be working on we're going to start off with section 3.3, graph sketching, asymptotes and rational functions. Oh, these are fun. So let me give a, a summary here. These can kind of take a while. Like they're not really difficult. They're not really complex. So I can't articulate this properly, but long story short, like there was a poster in the hallways of Morehouse when I was a student there, and it says something along the lines of, there is no such thing as complex. What we consider to be complex is just a long string of simple ideas. And so that's exactly what's at play here. When we're doing curve sketching, It's just a long string of simple ideas. When we try to see the whole thing in totality, it's very easy to get overwhelmed. I try not to use that word, but it's easy to get overwhelmed. But if you just break it down into part by part, bit by bit, brick by brick, and the individual parts within and of themselves are simple. So if you can get each individual little part, then you string them together in one long chain, and that's the idea of what's going on here. Honestly, that's what a lot of mathematics is. Honestly, that's what a lot of life is. When you look at the totality, it's overwhelming, but if you break it down into small digestible pieces, there's nothing you can't do. I mean, to be honest, that's really what it is. As long as you can do step by step, brick by brick, you can build mansions one brick at a time, for real. So anyway, so objectives here. So one, we like to find limits involving infinity. The two, determine the asymptotes of a function's graph. And three, graph rational functions. Okay. So a rational function is a function f that can be described by some p of x over q of x, where p and q are polynomials, with q of x not the zero polynomial, because again, we cannot divide by zero. The domain of f consists of all inputs of x, which q of x is not zero. So in other words, the domain of a rational is all reals except any x that makes the denominator zero. Okay. So the line x equals a is a vertical asymptote if one of the following statements are true. So the limit as x approaches a from the left of f of x tends to infinity. That's a vertical asymptote. These are all examples of vertical asymptotes. The limit as x approaches a from the left of f of x equals negative infinity. So as we approach some x value equal to a from the left or the right, if the y value goes to either positive infinity or negative infinity, we consider those vertical asymptotes. Same thing coming from the right. If as the limit as x approaches a from the right of f of x, if it tends to either positive infinity or negative infinity, then that's indicative of a vertical asymptote. Okay. So the graph of a rational function never crosses a vertical asymptote. If the expression that defines the rational function is simplified, meaning that it has no common factors other than -1 or 1, then if a is an input that makes the denominator 0, the line x equals a is a vertical asymptote. So long story short, what this is saying is like, okay, if you have a rational function and you have some value of x that gives you like some k over 0, like some number other than 0, some k over 0, then that's going to be a vertical asymptote. I'll just say this as a disclaimer. If a value of x gives you 0 over 0, that's not going to be a vertical asymptote. That's going to be a hole or a gap in the graph, right? Let me kind of do this real quick. So, for instance, what I mean by this, if k is some real number other than 0, some number over 0, that's a KO, that's going to be your vertical asymptote, right? So another one is if you have 0 over some number, this is okay. That's going to be equal to 0. And then lastly, if you have 0 over 0, that's a hole or a gap. Hole or a gap in the graph. All right. So the vertical asymptote is going to be when we have some number over 0, right? But again, if we have 0 over 0, that's a hole or a gap. So those are the three kind of scenarios there. Okay, let's see what else we got. Okay. The vertical asymptote of the function. Okay. All right, so we're fortunate here because this was already in factored form. So let's identify our zeros. Like, okay, so we see that when the zeros are the denominator are what? When x is what? 0, 1, or -1, right? If x is 0, it makes, okay, so when x is 0, I think it gives 0 over 0. So that's going to be a hole or a gap. That's going to give us 0. Let's see, f of 0. That's going to give us 0 over 0. So that's going to be a hole or a gap. So that's not a vertical asymptote. Let's look over here. So then when x is 1. So then f of 1, what is that? Like it's basically going to be some negative number over 0, right? So that's a vertical asymptote. Right? You can find a specific number. The main takeaway is that we have some number other than 0 over 0. So that means we're going to have a vertical asymptote when x is 1. And then lastly, when x is -1, let me see. It's going to be what, some positive number over 0, which is still a vertical asymptote. Okay. All right. So the vertical asymptotes are going to be what, x equals plus or minus 1. Okay. So we were able to successfully identify vertical asymptotes. And x equals 0 was a bait. That should be a hole or a gap in the graph. Okay. Since 1 and -1 make the denominator 0, these are vertical asymptotes. Now, what they ended up doing, they canceled the x's, right? They had the x's on the left that can cancel. They canceled those guys right here. So this canceled that. That's why I didn't show up in there finally. Okay. I'll leave the quick check for you all. Okay. So the line y equals b is a horizontal asymptote if either or both of the following statements are true. So the limit as x tends to either negative infinity or positive infinity of f of x equals b. So in other words, what we're saying is, as our original function goes off to either the far right or the far left, if it approaches some number y, then that's what we call our horizontal asymptote. The graph of a rational function may or may not cross a horizontal asymptote. So like how we cannot cross the vertical asymptote, it may or may not cross the horizontal. Horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. The degree of a polynomial in one variable is the highest power of that variable. Let me see. Okay, let's just see it in action. Okay, the horizontal asymptote. There are actually two different ways that we can go about this. I'll just recap this real quick from college algebra. You may or may not have heard this. I'll just say it just to mention it. So in college algebra, when we're doing horizontal asymptotes, we use a 3-prong test where you compare the degree of the numerator. So I put it in purple because I'm just mentioning this from college algebra. So for the horizontal asymptote from college algebra, it's a 3-prong test. First, if the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is going to be what? Y equals 0. Okay. If the degree of the numerator is equal to the degree of the denominator, your horizontal asymptote is going to be the ratio of your leading coefficients. So your AN over BN, something like that. Basically, the ratio of your leading coefficients. And then the third case, if the degree of the numerator is larger than the degree of the denominator, then there's some other cases. But for right now, we'll say no horizontal asymptote. Now that's just from college algebra. So you could use that if you want. And then the alternative here. So I'm going to showcase, I think, a technique that's a little bit better for this course, right? So we want to determine the horizontal asymptote of this guy. So what we can do, we're going to factor out the highest power of x, right? So, and like you might be able to see, okay, is this case 1, 2, or 3? But I'll let you do it on your own. So what we're going to do is factor out x squared from all terms from the top and bottom, right? So if we factor out x squared from the numerator, we're going to be left with what? 3 plus 2 over x minus 4 over x squared. And then it's going to be x squared here. And we're going to have 2 minus 1 over x plus 1 over x squared. Okay. So then this is going to cancel this. So now when we consider the limit as x tends to positive infinity of this guy, right? Of the above part. Matter of fact, let me just move this over. So again, when we take the limit as x tends to infinity of what's left over, what happens? So this, like, if you focus on this guy here, right? So want to kind of play with a few numbers, all right? So when x is 1, right, what answer do we get for that term that's circled? We get 2. When x is 2, we get 1, right? When x is 4 over 5, when x is 20 and bigger, you should notice something about the an expanding denominator. So with that expanding denominator, as x goes off the and we're back, right? So again, when we have a fixed number over ever expanding denominator, that term tends to 0. So if you can understand the concept behind that one term, these remaining terms behave in a similar fashion. So as x goes off to positive infinity, those guys tends to 0. So then now only thing that's left is 3 over 2. So then what we're saying is that the horizontal asymptote, as x goes to either positive infinity, now you can show a similar result as x goes off to negative infinity, right? Now, if we use college algebra, we can say, oh, well, the leading coefficients, the degree of the numerator is equal to the degree of the denominator. So the horizontal asymptote is going to be the ratio of the leading coefficients, which is going to be our 3 over 2. So you can use either technique. For our purposes, you factor out the highest power of x, so they cancel, and then take the limit as x tends to infinity, and the black and blue is a little bit more accurate. But you can use the purple, whichever one floats your goal. All right. Take the limit as x, and again, negative infinity, positive infinity, we get the same result. So therefore, y equals 3/2 is the horizontal asymptote. Okay. Quick check I'm going to leave for you. Let's look at this. So a linear asymptote that is neither vertical nor horizontal is called a slant or oblique asymptote. So I think in that college algebra example where we had case 3, where the degree of the numerator was larger than the degree of the denominator, this is one of those special cases. It's not a horizontal, but if the degree of the numerator is larger than the degree of the denominator by 1 degree, then that's when we're going to have this slant or oblique asymptote. So for any rational function of the form p over q, a slant asymptote occurs when the degree of the numerator is exactly 1 more than the degree of the denominator. A graph can cross a slant asymptote. So it can cross the slant asymptote, it can cross the horizontal asymptote, but it cannot cross the vertical asymptote. So if we wanted to find the slant asymptote, one, notice that the degree of the numerator is larger than the degree of the denominator by 1 degree. And essentially we do polynomial long division here, right? So I think that's from college algebra as well. We could factor, does that help us? I'm just going to do polynomial long division. We're dividing by, okay, so if we're going to do polynomial long division, we got this x minus 1. I'm going to do my placeholder. So I got x squared, I need a placeholder. We're going to say plus 0x. And then minus 4. So then when we go to do polynomial long division, we say the first divided by the first. So then x squared divided by x. Now I line up my like terms. On the diagonal, we multiply. So that's going to be x squared minus x. And then we need to distribute a negative. So that's polynomial long division. You might have to review that. Okay. Combine like terms. Go ahead. It cut off again. Oh no. What? How is this the case? Oh, come on, Morehouse. Why is it doing this all of a sudden? I think they changed their stuff. Because I'm definitely logged in. Man, this is not good. I got to figure out how to get around this. Okay. Okay. Well, we're going to do the best that we can. I'm going to have to contact IT. Let me see. So I just got a notification that says your free trial is about to end. So I've been using Zoom for like years now. I ain't never had this problem. I think that Morehouse may have done something or changed some kind of setting to where now we don't have the full version anymore, which doesn't make sense if we're going to be using this. So I gotta reach out to them. If we get cut off, I'm going to have to default to my recordings. And on Wednesday, hopefully I'll get a result by Wednesday. We're still in 3-3 right now. So then for today, you still need 3-3 and 3-4. On Wednesday, Hell or High Water is 3-5 and 3-6. And then, hopefully again, before then, we can get all these technical difficulties resolved. Okay, anyway, so let's just kind of power through. Hopefully it doesn't cut off on us. So if we add, we get an x here, and then the 4 comes down. Okay. So then we say the first divided by the first again. So x divided by x is a 1. And we multiply, it's going to be x minus 1. We should distribute our negative. Combine like terms, we get a remainder of -3. Okay. So let me think. So then what we're saying is that this original part is going to be equal to x plus 1 minus 3 over x minus 1. Let me think. Okay, that's fine. So then the equation of the slant asymptote is this guy right here. Okay. So our slant asymptote is going to be what? Y equals x plus 1. Right? So once we do the polynomial long division, dividend, divisor, our quotient, our answer to x plus 1 is going to be equation of our slant asymptote. So the x is to find the slant asymptote. We got y equals x plus 1.
Damn.
All right, let's make sure.
Oh, no, that the one.
I ain't show you that one.
Nah. No, I love the chocolate. Oh, man.
Okay. All right. So I think we're okay, right? So the equation of our slant is going to be y equals x plus 1, right? So from polynomial long division, we got that guy. I think we're good. So this should be the result. This is what they were asking us to find. All right. Polynomial long division, x plus 1, same thing. We can see that its absolute value of x is very large. That tends to 0, right? Some fixed number over an ever-expanding denominator. So as x tends to either positive infinity or negative infinity, our function gets closer and closer to x plus 1. Okay, so that wasn't too bad. We got about 10 minutes left in this section. We got a ways to go. I'm going to leave this as an exercise, okay? Exponential and log functions. Okay, I'll kind of go through this one a little bit. So asymptotes of exponential and log functions. Generally speaking, exponential functions have horizontal asymptotes. Log functions have vertical asymptotes, okay? Exponential, let me say that again. Generally speaking, exponential functions have horizontal asymptotes. Log functions have vertical asymptotes. An exponential function of this form, where b is positive, has a horizontal asymptote, y equals 0, which is the x-axis, as x tends to negative infinity. So as we go to the far left, the x-axis serves as a horizontal asymptote. Let's see. So that's where our b was positive. So the second part is a repeat, but now our b is negative. So then as x goes off to positive infinity, the x-axis serves, or y equals 0 serves as a horizontal asymptote. For the log function, it has a vertical asymptote at x equals a as x approaches a from the right. So a log function, basically the y-axis serves as our vertical asymptote as we approach the y-axis coming from the right, generally speaking. And then, so I think with the third option, we had the log of x minus a. The fourth option, now we reverse those. The log of a minus x is going to have a vertical asymptote, x equals a, as x approaches a coming from the left, okay? We're going to see how we can kind of find those. Find the horizontal asymptote. Okay. So this one should be exponential. Let's see what happens as x goes off to either positive or negative infinity. Now we have a negative power, right? E to a negative power. So as x goes off to positive infinity, I'm going to rewrite this guy. I'm going to rewrite it. So this f of x, I guess we're still okay. So if that's a negative power, we can rewrite it as 1 plus 25 over e to the power of 0.04x under 200, right? So as x goes off to positive infinity, we're going to have a fixed number over ever-expanding denominator. So that means that this guy, this whole thing here, tends to 0, right? So as x goes off to positive infinity, let me think. Horizontal. It looks like we're approaching So we'll say the limit as x tends to positive infinity of f of x. It's like it's 200 over 1, which is just 200. Let me think. Mm-hmm. You have a question going once, going twice. Okay. Negative infinity. That flips. Okay. So as x goes off to the far right, this function approaches 200, right? What about as x goes off to the far left? The limit as x tends to negative infinity of this function. Okay. So if we're going to negative infinity, then we have a double negative becomes positive, which means that we're going to have something like it's essentially going to be 200 over some really large number. All right, this one is behaving a little bit different than the first one, which this is essentially 0. So what this is saying is that as we go off to the far right,